All right, guys, I hope you have had a good day so far and are ready to do some math. Today is an important lesson. It's going to come up all year long. It's something you're going to use next year quite a bit, but it is not an easy lesson. This is fairly long. I'm going to try to have it so that if you get the answers right as you're trying these, you can skip as much of this video as possible. It's going to take me hours and hours to make that true, but I will do it because I want this to be as short for you as can be done while still having you learn it. Our goal is we are wanting to continue to transform the parent functions of the form y equals f of x, but we're going to do even more than we've done before. Today we're going to be looking at a bunch of different transformations, and I want to make sure we have this language. Vertical is up and down. This is vertical is things that are up and down. Horizontal are things that are left and right. Stretch, the word stretch is when you take something and you pull it apart. You stretch it like this. And compress is when you take something and you squeeze it together. You push it in like this. Okay. So stretch is when you pull something apart, pull it out further, and compress is when you push something in. And a reflection is when something switches side across an axis. Okay, so let's make sure we're all on the same page. We're going to start with a warm-up of stuff you should already be familiar with. Go ahead and try to say what is the equation of f of x. And hopefully you notice that this is an absolute value parent function. It has a vertex at the point 3, 2. The parent function of absolute value normally has a vertex at 0, 0. And this was translated 1, 2, 3 to the right and 2 up. And the way we do that is we write, I guess this is f of x. We need to write f of x equals. The Descamon is a little shaky. I apologize if I'm not at school, which is unfortunate. So the desk shakes sometimes, and so sometimes the camera shakes when I move, and I'll try to minimize that, but I apologize if that's the case. So we've got an absolute value function. It got shifted 1, 2, 3 to the right, and we do x minus 3 to shift it to the right. Remember that horizontal shifts are backwards from what you might think. So even though it's at positive 3, we have to do x minus 3. Plus 2, this is a shift up. So this minus 3 makes it a shift to the right, and the plus 2 shifts it up, and it's an absolute value function. Okay? Go ahead and write the equation for g of x. Hopefully you got g of x equals. We should recognize this is a square root function. There is nothing in the domain off to the left, and it has a vertex at the end of it. It's also got a concave shape. In this case, it's concave up. Now we should notice that this is reflected from the square root parent function. So we need a negative in the front. Negative square root of, here's the vertex. It got shifted 1 to the left. And so inside of the square root, we need x plus 1. Remember, that's backwards to make it shift to the left. And we need the vertex to shift up by 2, so plus 2 outside of the square root. And if you haven't been able to tell, we're going to be using some parent functions. We need to know our parent functions pretty well, so let's make sure we feel comfortable with those. I'll be going back and forth between this sheet all day. We should know our absolute value parent function. It has a vertex at 0, 0. A quadratic parent function, y equals x squared, and has a vertex at 0, 0. A cubic parent function, y equals x cubed. A square root parent function, which has a vertex at 0, 0. And a cube root parent function, which has a point at 0, 0. You might notice they all have an important point at 0, 0, whether it be a vertex here, here, and here, or an inflection point on these two. It's not a vertex, it's a place where the concavity is changing from concave down to concave up, or concave up to concave down. There is one other point besides 0, 0. So 0, 0, all of these have, and we're going to make use of that today. But I want you to look very closely, and all of these graphs have another point that all of them share. What is that point? And hopefully you saw that all of these functions have the point 1, 1. And this is because 1 to the third power is 1, the square root of 1 is 1, the absolute value of 1 is 1, the cube root of 1 is 1, and so we end up with this point at 1, 1 on all of them, and we're going to make use of that today as well. So Let's remember what we should already know. We're going to be using this equation, y equals a times f of x minus h plus k. And we should already know that k is a vertical translation by k units. H is a horizontal translation by h units. And remember that the h is backwards. That's why it's x minus h here. So if it's like x minus 5, that's a shift to the right by 5. And a is if the a value is less than 0, in other words, if a is negative, if we have a negative sign in the front, that will be a reflection across which axis? It's a reflection across the y-axis. It's a vertical reflection. Oh, sorry. Oh my goodness. The x-axis. It's a reflection across the x-axis, which is a vertical reflection. So that reflects this way vertically across the x-axis. But we have two new things we're going to do. If, and this is a little weird, the absolute value of a is more than 1. This means the absolute value is because we don't care whether it's positive or negative, and absolute value takes whatever's inside of it and makes it positive. So for instance, the absolute value of 3 is 3. The absolute value of negative 3 is also 3. And we're just looking at the size of these numbers. We use absolute value when we care about the distance from 0 and not necessarily whether it's positive or negative, and that's what's going on here. If the size of the number, the absolute value of the number, is above 1, so if that number is 3 or negative 7.2, those both have a size above 1, even though one is positive and one is negative, f of x is vertically stretched by a factor of a. So this is what's going to make something get stretched vertically. So up and down. It's like we take something and we pull it up. On the other hand, if the absolute value of a is less than 1, so it doesn't matter if it's positive or negative, it's about the size. So a could be 0.5, that's an absolute value less than 1, or negative 1/3, those are both absolute values less than 1. F of x is vertically compressed. And we will see why when we get to the numbers in just a minute. And that means that the function compressed means kind of compressed together, and vertically compressed means it's like if we took our fingers and smushed it down this way. Okay, so let's get into some numbers and have this make more sense once we actually do have numbers. And I'll keep this at the top. Oh, by the way, I've started using green for things that are not like example problems, but rather information we're going to want to come back to over and over again. So I'm going to try to box in green information that we might want to come back to over and over again. And I will try to be consistent about this as the year goes on, but it's new for me. I did it because I realized when I was watching one of my other videos that it's a little jarring seeing papers shuffle. So I will try to be better at that. So let's look at the parent function. Y equals the absolute value of x. And here's our parent function, y equals absolute value of x. It has a vertex at 0, 0. It's got these points here. All right, this is what it looks like. This is the parent function. What happens if I put a 3 in front of the absolute value sign? Well, what's going to happen is I'm going to do the absolute value of x and then take all of those y values and multiply them by 3. Let's look what this looks like in the table. So if x is negative 2, g of negative 2 is 3 times the absolute value of negative 2. Absolute value of negative 2 is 2, and 3 times 2 is 6. So when x is negative 2, the y value is 6. Okay? When x is negative 1, we do the absolute value and get positive 1 and multiply it by 3. When x is 0, absolute value of 0 is still 0. 3 times 0 is 0. And absolute value of 1 is 1. 3 times 1 is 3. Absolute value of, when x is 2, absolute value of 2 is 2. 3 times 2 is 6. And what this looks like on a graph is we still have a vertex at 0, 0. Notice that the vertex did not change. Because when we have a y value of 0, multiplying it by something will not change it. Anything times 0 is still 0. So the points at 0, 0 in all of our functions today will not change when we multiply them by something. Okay? On the other hand, the point at 1, 1, is now 1, 3. And that's because the y value got multiplied by 3. The point at 2, 2 is now 2, 6. And that's because the y value of 2 got multiplied by 3. To the left, the point of negative 1, 1 got multiplied by 3. The point negative 2, 2 became negative 2, 6. It got multiplied by 3. And I hope we can see why we call this vertically stretched. It's like we took this one and stretched it out vertically. We took our absolute value and stretched it out, and that's what's happening here. All the y values are 3 times higher than they were before. We say this is vertically stretched by a factor of 3. Okay, so that is what happened here in g of x. Let's look at our second example. H of x equals negative 1/2 x cubed. And this time, I notice there's a negative in front and a 1/2. And so first I'm going to look at the effect the 1/2 has. This is a vertical compression by a factor of 1/2. All of the y values will get multiplied by 1/2. And I'm not going to make a whole table this time. I'm just going to look at what happens. Here the y value is 0, and 0 times 1/2 is still 0. That point won't change. Here the point is 1, 1, and that y value is 1. When we take 1 and multiply it by 1/2, the new y value will be 1/2. 1 times 1/2 is 1/2. The next point would be up here at 2, 8, because 2 times 2 times 2, 2 cubed is 8. When the y value gets multiplied by 1/2, half of 8 is 4. And so it ends up looking like this. On the left side, we also end up with negative 1, negative 1/2, because negative 1 cubed is negative 1. Half of negative 1 is negative 1/2. And compared to the parent function, what happened here was this cubic function got compressed in. It's half as high at every point as it used to be. So this point where it used to be at 2, 8, it was like off the graph, it was way up here, is now at 2, 4. And so all the y values are half as high. Pay attention especially to this point at, remember I said that all of the parent functions had a point at 0, 0 and a point at 1, 1. This point at 1, 1, we can always get by just multiplying by that value. So look, this point at 1, 1 became 1, 3 because the y value of 1 got multiplied by 3. This parent function also had a point at 1, 1, and when we multiply that by 1/2, it becomes 1, 1/2. So if you always go to the right by 1, you can multiply by that number. Okay, there was one more thing going on here, which was this negative. Remember that a negative in front multiplies by a negative 1, and so it will be a reflection across the x-axis. So there are two ways to think about it. We could take this 1/2 x cubed and reflect it. 0, when 0 gets reflected, it's still at 0. When 1, 1/2 gets reflected, it will now be at 1, negative 1/2. When 2, 4 gets reflected, it will now be at 2, negative 4. What we will usually do is just kind of go from the parent function. 1, 1, 1 is getting multiplied by negative 1/2. 2, 8, 8 is getting multiplied by negative 1/2. 8 times negative 1/2 is negative 4, and that's down here. Oops. There's normally a point at negative 1, negative 1. That gets multiplied by negative 1/2. Negative 1 times negative 1/2 is positive 1/2. And negative 2, negative 8 is where this other point was, and negative 8 times negative 1/2 is positive 4. And so we can see it got both vertically compressed and reflected. This vertical reflection, hopefully we can see this part that was up is now down, this part that was down is now up, and the points got reflected. Okay, let's take this and see if we can find what the equation is of a graph. What is the parent function here? Hopefully we can tell this is a cube root parent function because it does have the same shape as a cube root. It has this concavity with an inflection point, but it's concave down to the right, unlike a cubic function, which is concave up. So it's not a cubic, it's a cube root because it's more horizontal. All right, so it's a cubic parent function. And what we're going to look at is this point. The vertex was not shifted in any direction. Not the vertex, sorry, the inflection point is still at 0, 0, and we're going to go 1 to the right. And when I go 1 to the right, I can see that this point is not up at 1, 1 where it normally is. It's at 1, 1/2. So what is the number we multiplied 1 by, which is what the y value would normally be? Remember, all of these have a point at 1, 1. But now, when x is 1, the y value is 1/2. So what do we have to multiply by? What's the multiplier to get us to 1/2? Well, it's very easy when you're multiplying by 1. That number is 1/2. And so f of x must equal, it's a cube root parent function, 1/2 cube root of x. The y values got multiplied by 1/2. So we can see that. All right, let's see how you can do. You can try this on your own. Remember that if a is negative, it will reflect across the x-axis. If a is above 1, the function will be vertically stretched. You just multiply the y values. And if a is less than 1, the y value will be vertically compressed. I don't know why I didn't finish writing that. Okay. So try this on your own. What is the equation of f of x? And hopefully we got it right here. We should recognize that this is the square root parent function. So f of x is, we know it's going to have a square root. The vertex is still at 0, 0, so it did not get, there's not going to be an h or a k here that shifts it. Instead, we're going to look at what happened to that point at 1, 1. Normally, square root of 1 is 1, but instead it's at 1, 3. So what number did we multiply by to go from 1 to 3? And that gives it away right away. We can look at that 1 point over and see what it got multiplied by. This is 3 times the square root of x. And if you really wanted to check another point, you could plug in x equals 4. The square root of 4 is 2. 2 times 3 gives us 6. So when you put in 4 for x, you will get 6 out for y. But you really can tell it just from that first point because all of these parent functions have a point at 1, 1. And so you just see what that point got multiplied up by. Okay, let's look at g of x. What is the equation of g of x? Well, we should notice right away that this is a quadratic because it makes a parabola. And we're going to look at the point that would normally be 1 squared would be 1. And instead, there's a point right here. This is at 1, 1/2. So this was vertically compressed. Y equals g of x, I guess I should say. Since we have a name, we should put g of x and not y equals. G of x equals 1/2 x squared. And I know this is a 1/2 because normally when I move over by 1 from the vertex, 1 squared would be 1, but it was only up by 1/2. So we always want to look 1 over from the vertex to be able to tell what's going on there. All right. So in words, we would write out that this was vertically compressed by a factor of 1/2. Okay. You are going to take a separate sheet of paper and you're going to have 7 graphs today that you're going to put on this separate sheet of paper. And so I want you to, on that paper, I don't want you to have to take a bunch of pictures. We're going to one at a time put these on the paper. And then at the end, you will take a picture of it and upload it. And it will count as a large point value problem. So I want you on your own paper to graph, starting with y equals 2 absolute value of x. See if you can do it on your own. Hopefully you did it right. We know it's the absolute value parent function, and the absolute value parent function has a vertex at 0, 0. And normally it makes a V shape with a point at 1, 1. But it got multiplied by 2. It's vertically stretched by a factor of 2. So instead of having a point at 1, 1, it will have a point at 1, 2. And it makes a V shape because it's the absolute value parent function. So we can just go up by a constant rate of change, up by 2, up by 2, up by 2 as we go over to the right. As we go to the left, every time we move to the left by 1, the y value will increase by 2 as well. And we know that because it's an absolute value parent function, which makes a V shape that has 2 constant rates of change. Hopefully you graphed it correctly. All right, let's look at this other one. G of x equals negative 1/4 square root of x. On your separate sheet of paper, graph g of x. Make sure you're labeling these. This one should be labeled f of x equals. This one should be labeled g of x equals. Try to have it well organized in some way, either like next to each other or going vertically. And let's see how you did graphing this. This is a square root parent function. We know it has a vertex at 0, 0. That 0 getting multiplied by anything is still 0, so the vertex will not change. This negative will reflect it. So instead of having a parent function that looks like this, here's that parent function. Notice that the green should give you a clue that this is just something we're referring back to. It's going to get reflected, so it will be opening down instead of up. It will be decreasing instead of increasing. And all the y values got multiplied by 1/4. So let's look at how that works. Normally, square root of 1 would be 1. It has that point at 1, 1. The y value of 1 gets multiplied by negative 1/4. 1 times negative 1/4 is negative 1/4. So there will be a y value at 1, negative 1/4. If you just drew a square root shape from here, that would get you most of the points, but we can do better. We can find another square root number we can do. We know that normally we would have a point at 4, 2. And so 2 gets multiplied by negative 1/4. So when x is 4, y would normally be 2. But when that y value gets multiplied by negative 1/4, 2 times negative 1/4 is negative 1/2. So when x is 4, 1, 2, 3, 4, y will be negative 1/2. And we can see that this square root function was not only reflected, but it's also vertically compressed. It's just going down very, very slowly. It's decreasing very slowly. Okay, let's move on to something a little bit more complex. What if we put everything we know together so far? What if we take our whole equation we should know here, y equals a times f of x minus h plus k, and put it together? Okay. Well, it's going to go exactly like you think it should go. This will be a shift to the right. This, negative 3, will be a shift down by 3. This will be a vertical reflection, and this will be a vertical stretch. So we can kind of think of what's going on here. Here's our a, our h, and our k. And what we're going to do is we're going to take what type of function it is. In this case, it's a quadratic. It's x minus 1 squared. So we know it's going to make a parabola shape. And we're going to start by moving the vertex. So we're always going to graph the vertex first. Okay. So the vertex, instead of being at 0, 0, is going to be a vertex or inflection point, depending on what type of function it is. So we're going to graph the vertex first. And the vertex, instead of being at 0, 0, got shifted right by 1 and down by 3. So that vertex will be at 1, negative 3. And now we know it's getting reflected, so instead of being concave up, it's going to be concave down and stretched by a factor of 2. So what I like to do here is, because we're multiplying by negative 2, I know there's normally this point 1 over from the vertex that's up by 1, 1, 1. Remember that on all of these parent functions, it's got this point at 1, 1. And so I can just take 1 and multiply it by negative 2. So negative 2 times 1 is negative 2. And so to the right of the vertex by 1, I will go down negative 2. And because it's a quadratic, I know that to the left it will also be down by negative 2 because it is symmetric. Remember, parabolas have an axis of symmetry. If I wanted to find another point, what I would do is I would go 2 over from the vertex and do 2 squared, which would be 4. And 4 times negative 2 would be negative 8. And so if I go 2 to the right of the vertex, I would count down by 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's off the graph here, but that's what I would do. Okay. What is the equation of f of x here? Okay, well, what we should notice is, what type of function is this? What is the parent function? We should know it's a square root parent function. So it's going to be f of x equals, and it's going to have a square root in it somewhere. The next thing I'm going to look at is the vertex. We're always going to identify the vertex first. And I see the vertex was 4 to the left and 2 up. So square root of x plus 4, that's 4 to the left and 2 up. Now the question is the square root of 1 1? This is where it would be normally. If it were the parent function, it would look like this, right? But it got reflected. I know I will need a negative. And did it get multiplied by anything? And the answer is yes, because it didn't go down by 1. It only went down by 1/2. And so I know I need a 1/2 here. So this is 1/2 square root of x plus 4. And I knew that by looking at where the vertex was. That's the 4 and the 2. And then looking at the first point to the right, it's down by 1/2 from the vertex. And so it tells me it's getting multiplied by negative 1/2. Okay? Why don't you try this on your own? See how you can do. What is the equation of g of x here? And we should get that g of x equals, this is a cubic parent function because we notice it has the same shape as the cubic parent function. So it's a cubic. The vertex is to the right by 3, so that needs to be minus 3 inside of the parentheses to make it go to the right by 3. Horizontal translations are to the right or left, and that goes inside of the parentheses. The vertical translation is up by 1. That inflection point is 3 points to the right and 1 up, and vertical translations go outside of the parentheses. The question is, was there a reflection or a stretch or compress? And the answer is, we can find that by going 1 to the right of the inflection point, and it's only up by 1/2. Since it's up by 1/2, I need to multiply all the y values by 1/2. It got vertically compressed. It did not get reflected. It's still increasing to the right side, and so we know there's no negative in front. Okay, now this is your third graph that you're going to graph on a separate sheet of paper. So on your separate sheet of paper that you already graphed, these two, you're going to be graphing on that same sheet of paper. You're graphing h of x equals -1/3 absolute value of x plus 2 plus 1. So hopefully you did well. We'll see. You should notice that it got shifted left by 2 and up by 1. Absolute value parent function has a vertex at 0, 0. When that gets shifted 2 to the left and 1 up, this will be the new vertex, and it's getting multiplied by -1/3. So it's going to reflect, so it'll open down, and when I go 1 to the right, it will go down by 1/3. And because it's an absolute value parent function, it has a axis of symmetry. Now, absolute value parent functions, this and linear are the only ones you can use this trick on. Since it has a constant rate of change, it can go down by 1/3, down by 1/3, down by 1/3. We can use the trick we use with linear functions, which is to go down by 1 and over by 3. That's the same as going down by 1/3, down by 2/3, down by 3/3 is down by 1 and over by 3. You cannot do this with quadratics or cubics, but you can do it with absolute value graphs. I want to make sure you are not graphing this on your paper after you see the answer. I really struggled with whether to give you feedback, and I decided it was more valuable and more important to you that you get to see did you get it right away than it was for me to make sure you weren't cheating. But I would ask that you do not write this down until this is just for you to check yourself. This isn't for you to copy down onto your paper. What should be going onto your paper is, did you do the graph yourself ahead of time? Okay, let's look at the next thing. All right, this is, I think, one of the trickiest concepts in all of Algebra 2. So, buckle your seatbelts, this is going to be tricky. Here we are multiplying x by a number. C, in general, is what we call it. This is different from multiplying on the outside. Just like when we added or subtracted something inside of the parentheses, it was a horizontal shift instead of a vertical shift. If we multiply by something inside the parentheses instead of outside the parentheses, it will have a horizontal effect on the graph instead of a vertical effect. So, if this number is less than 0, which means it's negative, if you ever see it's negative, it will be a reflection just like it was when there was a negative on the outside. It will be a reflection, but instead of being a reflection, a vertical reflection, it will be a horizontal reflection. It will reflect across the y-axis, okay? If this number is above 1, the absolute value is above 1, so again, we don't care if it's 3 or -5/3, these numbers are both have an absolute value bigger than 1. Just because this is a fraction, it's still -1.66666. It's bigger than 1, the absolute value of it is. And we don't care whether it's positive or negative for the compression or stretch part, we care the size. Now, this is backwards from what you might think. If the number is bigger than 1, it is going to be horizontally compressed. So we're going to take it and we're going to horizontally compress it if this number is bigger than 1. And if the number is smaller than 1, if the absolute value is less than 1, then we will horizontally stretch it. And we'll see why that's backwards in just a second, but it's weird. So this is backwards from what you might think, just like the h was. Remember the thing inside the parentheses when you added or subtracted, that was backwards. When you multiply inside the parentheses, that is also backwards from what you might expect. Let's look at an example. If g of x is equal to 1/3 x squared, notice that the 1/3 is in parentheses. This does not equal 1/3 x squared. This is not the same thing. Here the x is getting squared and then multiplying by 1/3. Here the x is getting multiplied by 1/3 and then being squared, and the order of operations very much matters here. So let's look at what happens. The parent function, y equals x squared, when we do -2 squared, we get 4, -1 squared is 1, 2 squared is 4, 0 squared is 0, okay? And this is the graph we get, right? 2 squared is 4, -2 squared is 4, all that stuff, okay? But what's happening is, because we are multiplying on the inside by by 1/3, we're multiplying inside the parentheses. This is a horizontal. You might think 1/3 would be a compression, but it is backwards. This is a stretch by a factor of, and we wrote up here that it's a factor of 1/c. It's the reciprocal of c. And for a fraction, you just flip the fraction. So it's a horizontal stretch by a factor of 3. That means that every x value will be 3 times further out from the vertex than it normally would be. So this x value is normally 1 away from the vertex. We take this and we horizontally stretch it out 3 times. Notice instead of being at 1, 1, it's now at 1, 2, 3, 1. The x value is 3 times. Notice that the x values get multiplied by 3. All of the x values are getting multiplied by 3. The y values aren't changing. This y value is at exactly the same place as this y value is, but it's 3 times as far out. We horizontally stretched it. Hopefully you can see that you took this parabola and we stretched it horizontally. We can see why we use that word. Now let's look at the math behind why that is happening. Y on Earth is multiplying by 1/3, stretching it out. And the answer is because it's what x value you need to get the original input. When x is -6, 1/3 of -6 is -2, and then that is being squared. So to get the same result that you would get from -2 being squared, the input has to be 3 times higher so that when you multiply it by 1/3, it gets you the same number being squared. -6, when you multiply it by 1/3, will give you -2, so that when you square it, it gives you the same output as before. For instance, if we had an input of 5 squared would be 25. For this one, the x value you would have to put here to get out 25, to have a y value of 25, well, the x value is going to have to be 3 times bigger than usual, 15, because we're first going to multiply it by 1/3. 1/3 of 15 is 5, and 5 squared is 25. And so notice that the x value needs to be 3 times bigger. You are going 3 times further to the right to get the same y values out, and that's why it's horizontally compressing. Okay, let's look at the second example. Our parent function is y equals square root of x. We see this square root function. And here we've got h of x equals square root of -2x. This negative is on the inside of the square root. So instead of being a vertical reflection, it is a horizontal reflection. And we can see that here. Instead of the parent function increasing to the right, it increases as we go to the left. The other thing that's going on here is this 2. So this negative is a horizontal reflection, or we could say reflection across the y-axis. So it got reflected, here's the y-axis, and it got reflected across the y-axis, reflected horizontally. This 2 is a horizontal, because it's inside. And remember, if it's bigger than 1, it will be a compress. It's backwards from what you think it would be by a factor of, we do the reciprocal of 2. The reciprocal of 2 is 1/2. And so all of the x values, instead of square root of 1 being 1, you only need to go over to 1/2 to get the square root of, to get the y value of 1. Instead of normally having to go over by 4 to get to 2, we only have to go to the left by 2 to get to 2. And the reason is, again, that x value is getting multiplied before you do the square root. So when we put in an x of -2, -2 times -2 is +4, and the square root of +4 will give us 2. Okay, so those are the two effects that are having. All right, let's see if we can put this into practice here. What type of parent function do we have here? Hopefully it's clear this is a cube root parent function. Its inflection point is still at 0, 0, so it didn't get shifted. But we can see instead of having a point at 1, 1, this function has a point at 3, 1. This point is 3, the y value of 1 happens 3 times further to the right than we normally expected. And so this is a horizontal stretch by a factor of 3. This point is also 3 times as far to the left as we would normally expect it on the parent function. Remember that point is at 1, 1 and negative 1, 1. And so now it's 3 times to the right and 3 times to the left. It's horizontally stretched by a factor of 3. And so what's our equation that makes it horizontally stretched by a factor of 3? Well, it's going to be f of x equals. We know it's a cube root, and we want to stretch it horizontally. Since it's horizontal, it's going to be inside the root. And to stretch it by a factor of 3, we actually need a factor of 1/3, right? Remember, it's backwards from what you would think. So to stretch it by a factor of 3, we need to multiply by 1/3 on the inside. And that's because when x is 3, we will do 1/3 of 3 and get 1, and then we'll be just doing the cube root of 1 to get 1. Okay? What is the equation of this one? And I want to point out there are 4 possible correct answers, which is crazy. One thing we could notice is that normally the parent, I'm going to do the parent function in red here. No, where are my red pens? The parent function would normally have points here. And so we want to think about what happened. Well, one thing we could think is that we can think of this as a horizontal compression. Instead of having this point at x equals 2, it was only at 1. So one thing we could do is we could write g of x equals, to horizontally compress it. Remember, we need to put it on the inside. And we multiply by 2 to horizontally compress it by a factor of 1/2. So 2 times x inside the absolute value. So absolute value of 2x. And this is correct, okay? But we could also think about it as being horizontally reflected across the y-axis because it's symmetric. Because it's symmetric, putting a negative on the inside doesn't actually change anything. And so this is also a possible correct equation. Because this point moving to here and this point moving to here, there was an axis of symmetry. This horizontal reflection doesn't do anything to this function. Now you may have noticed another way to think about it is not as a horizontal compression, but rather a vertical stretch. This point is 2 times higher than this point at 1, 1, and so it's also okay to think of this as 2 times the absolute value of x, which is 2 times the y values of before. Notice this is on the outside now, so it's a vertical stretch is what it's doing. The last possibility is not -2 absolute value of x, because a negative on the outside would reflect it vertically, but it is fine to put 2 times the absolute value of -x, because a negative on the inside of the absolute value will reflect it horizontally again, and that horizontal reflection doesn't do anything for an absolute value function. Okay, so that's a little bit weird. Let's see how you do trying some of these on your own. Again, this is one of the hardest topics in all of Algebra 2. Let's see how you do. What is the equation for this function here? You should have noticed it was a square root equation. So I'm going to put y equals the square root. Now the square root parent function normally opens to the right. This was reflected horizontally, and so it needs to have a negative inside of the square root. Was it horizontally stretched or compressed? No. The square root of 1 is 1. We've got that point that was at 1, 1, and it got reflected directly, and so there's no numbers we need to multiply here. So it's just square root of -x. Here we have another function. Hopefully you can find it on your own. The equation is y equals, we should notice this is a cubic function. It is a transformation of the cubic parent function. And so I know it's going to have an x cubed in it. I see that this point is not at 1, 1. Normally there's a point where 1 cubed is 1. This point at 1, 1 was horizontally compressed by a factor of 1/2. And so to make that happen, since it's horizontally compressed, it needs to be inside. And because it's inside, it's backwards from what we would think. It gets multiplied by 2. 2x cubed. Notice, unlike the absolute value where multiplying by 2 on the outside and multiplying by 2 on the inside are the same, this is not correct. This would be a vertical stretch by a factor of 2, and it's not the same. Okay, let's look at our third one here. And our third one is a quadratic. And so hopefully you got the equation that this is y equals something squared. And there was no vertical reflection. I could think of this as a horizontal. So instead of having a point at 1, 1, it was horizontally stretched by a factor of 2. This point is 2 times further away than normal. So instead of being at 1, 1, this point is at 2, 1. So the x got multiplied by 2. And it's backwards on the inside because anything that's happening on the inside of the function always ends up backwards. So y equals 1/2 x squared is correct. However, it could also be a horizontal reflection, negative 1/2 x squared, because it's symmetric, and so a reflection horizontally doesn't do anything. If we really wanted to, we could think of this as a vertical compression. And if we were to do this, it would be 1/4 x squared. And I know that because this is not quite at 1/2. And going here, normally the point would be at 2, 4, and now the point is at 2, 1. The y value is getting multiplied by 1/4. So if I want it to be outside of the parentheses, it's not a 1/2, it's a 1/4. And there was one more option, y equals 1/4 times negative x squared, because this would be a vertical compression by a factor of 1/4 and a horizontal reflection, but the horizontal reflection doesn't do anything here. Okay. All right, on a separate sheet of graph paper, try graphing this on your own. F of x equals square root of 1/3 x. You should recognize that this is a horizontal stretch. Remember, it's backwards by a factor of 3. And so the graph is going to be the same as the square root parent function. So here's the square root parent function. 0, 0 is still going to be at 0, 0. But the point 1, 1 will happen 3 times further to the right. So it will happen when x is 3 and y is 1. So we end up with a square root graph that looks like this, okay, with a point at 3, 1. Horizontally stretched by a factor of 3 because of this 1/3 on the inside. And your next one to try is negative 2x cubed. Hopefully you were able to get it. This is a cubic parent function. This negative is a horizontal reflection. So instead of going like this, it will go to the left. And this is a reflection. And the 2 is a horizontal compression, backwards from what you might think, because it's on the inside. And so it means that instead of being at negative 1, 1, which would be if it was reflected, it'll be at negative 1/2, comma 1. And we know it's a cubic, and so it ends up looking like this on the other side, only at 1/2. Oh man, negative 1/2, comma 1. See, it's hard, guys. I almost messed it up there too. So we end up with a cubic like this with points at negative 1/2, comma 1, and 1/2, comma negative 1. Okay, we're almost done. We're going to put everything together here. And Jesus, I'm tired. So I'm sure you guys are exhausted from this too. This is a very important lesson, especially for next year's stuff. So let's make sure we understand it. It's also important for physics. Let's put everything together. If we have a number outside multiplying, a number inside multiplying, a number inside adding or subtracting, and a number outside adding or subtracting, what do each of those things do? We should know that K is a vertical shift, or translation, we can say it. H is a horizontal shift. So when we add or subtract something from x or y, it shifts the function, especially the vertex there. Sorry about this glare. I realize there's this like white square. It's because like the light, maybe I can adjust this. Maybe this is better. Sorry, there's some light coming in weirdly. It's the afternoon. So shifts come from adding or subtracting something, horizontal if it's inside, vertical if it's outside. The number on the outside multiplying can reflect if the number in front is negative. It can vertically stretch or vertically compress. Here it's when absolute value of A is bigger than 1. Here it's when absolute value of A is less than 1. So if those numbers are really big, the y's will get multiplied. If the numbers are really small, the y's will get multiplied by a smaller number and become smaller. C is the new one on the inside, and it can reflect just like A could if the C is negative. And it is a horizontal stretch if C is less than 1. So it's backwards than what we might think. And a horizontal compress if the absolute value of C is greater than 1. So notice that H and C are both on the inside, and they're both backwards from what you might think. H and C are both horizontal things. A and K are both vertical things. And so there's some sense there. Let's see how we do. Oh, we're almost done. I'm so excited. I'm so tired. All right. Whew. All right. What are the three things we have happening here in this graph? We have 2 on the inside getting squared. Notice that 2 is inside of this parentheses getting squared. Okay? So it's going to be horizontal. This plus 5 is on the inside. This minus 3 is on the outside. So here's C, not A. This is a horizontal multiplier. H is our shift left or right, and K is our shift up or down. The K is a shift down by 3. Our H is going to be a shift left, remember it's backwards, by 5. And our C is going to be a horizontal, is it stretch or compress? Well, remember it's backwards, so it's compress here, by a factor of 1/2. And so let's look how to graph this. What we will do is, just like earlier in the day, we will always start with the vertex or inflection point. In this case, it's a vertex. And the vertex normally would be at 0, 0. It's going to shift left by 5 and down by 3. So here's my vertex. This is a horizontal compression. So instead of being 1 over and 1 up, that point 1, 1 that we're used to having, it will be only half as far over, right? So 1/2 comma 1. Instead of having a point that is 2 over and 4 up, it will be only half as far over. So you only have to go 1 over for it to go 4 up. You got horizontally compressed. It got squeezed in by a factor of 1/2. All of the x values are half as far away from the vertex as they would normally have to be. So this is like 1/2 comma 1 away from the vertex. This is 1 comma 4. So 1 over and 4 up. Instead of normally it would be 2 over and 4 up. So you can see that that x value got divided by 2 from where it normally would be. All right, this is a square root function. Hopefully we can see what letter each of these things is. And again, we're talking about our general equation here from the last page. I'm going to go back to it, put this right here so you can see it. So here's our general equation. So what is this negative on the front? What letter is that? It's A. What parameter is this negative on the inside? That's C. What parameter is this plus 4 here? Well, it's getting added or subtracted on the inside. That's H. And the plus 1 is the K. So the plus 1 shifts 1. Oh, I don't know. It shifts 1, shift by 1 up. I don't know what I was writing here. The H shifts 4 to the left. This A reflects across the x-axis. It's a vertical reflection. So this negative in front reflects across the x-axis, and this negative on the inside reflects across the y-axis. It is a horizontal reflection. And so what's going to happen is we have our vertex that is 4 to the left and 1 up. And instead of having the normal square root parent function that looks like this, it got reflected across the x-axis and the y-axis. It got reflected both ways. So instead of going to the right, it will go to the left. Instead of opening up, it will open down. And so what our graph will look like is this. So it can go left 1, 2, 3, 4, and down by 2. Notice that it got both from the parent function, which would normally look like this, it got reflected vertically and horizontally. Okay. All right, a couple more examples because I think these are tricky. You guys can walk me through this. Where will the vertex be for this absolute value function? Hopefully we were able to get that it's at 1, -5. And that's coming from it's a shift to the right by 1 and down by 5. This 2 is doing what? Well, it's vertically stretching by a factor of 2. So normally the point 1, 1 would be 1 over and 1 up. Vertically stretching by a factor of 2 multiplies the y value by 2. So that would be like if it was at 1, 2. Okay? What does this negative do on the inside? That is a horizontal reflection. However, because this is absolute value and absolute value is symmetric, when you do a horizontal reflection, it's still the same. It doesn't do anything. So we can kind of ignore this here because it's in an absolute value function. So when you do a horizontal reflection, it doesn't change anything. This 3 on the inside, what is it doing? Well, this is a horizontal compress by a factor of 1/3. All the x values will get multiplied by 1/3. So this x value is getting multiplied by 1/3. So the y values got multiplied by 2, and the x values get multiplied by 1/3. So when we go over by 1/3, we go up by 2. When we go over by 1/3, we go up by 2. When we go over by 1/3, we go up by 2. It's kind of a nuts graph. It got both vertically stretched and horizontally compressed. And when we get to absolute value functions, we can talk about how to combine those. All right. Whew, guys, where is the vertex of this graph? Well, it didn't get horizontally shifted left or right, so it'll be at 0, 2. It got vertically shifted up by 2. It did not get horizontally shifted, and so the vertex is at 0. Oh, no, sorry, it's not a vertex. It's an inflection point because it's a cubic. The inflection point will be at 0, 2. This negative in the front will reflect vertically, and this 1/2 will horizontally stretch by a factor of 2. So normally we would have the point 1, 1 up from here. Horizontally stretched means the x values will get multiplied by 2. So it'd be like 2 over and 1 up. So instead of being 1 away, it's 2 times further away. But we also have that negative in front, so it gets reflected vertically. So stretched by 2, 2 to the right instead of 1 to the right, and reflected vertically will make it go down instead of up. So it looks like this. And to the left, it will be the same thing. It got stretched here, and the point that would have been at -1 got reflected up. So this is our cubic function. Man, tough stuff. All right, let's see. What are the equations here? So this is a square root function. Hopefully we recognize that. The vertex is at 0, 1. So it must have gotten shifted up by 1. Okay. I can see that it was reflected horizontally, not vertically, because the parent function would normally look like this. It got reflected horizontally, and so there's a negative on the inside. I have 2 possibilities here. I have this point. It is not 1 over and 1 up, so it did get stretched or compressed in some way. One way to think about it is that the point right here got horizontally stretched by a factor of 4. And so one way to do that is to put y equals the square root of, to make it stretched by a factor of 4, it's backwards. So this is negative 1/4 x plus 1. We need the negative to make it reflect, and the 1/4 horizontally stretches it by a factor of 4. Or we could think of it as vertically compressed by a factor. This is half as high as normal. So it could be 1/2 the square root of negative x plus 1. These are both considered correct. Notice that they both have a negative on the inside. That is necessary because we needed to horizontally reflect it. But we kind of can choose whether we think of it as a horizontal stretch or a vertical compression. All right. This last one we're going to do together, this is our last equation. What is this graph's equation? What is the vertex? Well, we can see it's at 3, 1. And so this is a quadratic. I can tell it is reflected. Is it horizontally reflected or vertically reflected? I can tell it's concave down, so it must have been vertically reflected. So I know I need a negative on the outside. X minus 3 squared plus 1. I know it's 3 to the right and 1 up. And there are two ways of thinking about it. It's really difficult to tell what it was vertically compressed by. And so I find it much easier to do this as a horizontal stretch. So this was stretched by a factor of 3. 1, 2, 3 to the right and 1 down. The first lattice point is 3 to the right and 1 down compared to where we normally are. And to horizontally stretch it, we need a 1/3 inside of the square. All right, guys. This is our last thing. This is for you to try. What is a correct equation of this graph? We're putting everything we have together here. And so I hope you're able to do this. Boy. The equation here should be y equals the square root. It's a square root parent function. I can see it got horizontally reflected, so there's a negative on the inside. This is x minus 3 because it shifted 3 to the right. This is 3 to the right, up by 1. And we can see it's not 1 over and 1 up, it's 1 over and 2 up. So that is a vertical stretch by a factor of 2. The 2 needs to be on the outside because it's vertically stretched by a factor of 2. And the negative needs to be on the inside to make it a horizontal reflection, not a vertical reflection. All right, this is the last equation that you're going to need to write down on your own. Go ahead and do it. Hopefully you got y equals, this is a cube root parent function. The vertex is, or not the vertex, the inflection point is 3 to the left. So that's x plus 3. And it is none up, so we don't have any plus or minus here. So 3 to the left, none up. And let's look at this next point. Normally we would expect it to be at 1, 1, but it's only half as far over. And so inside there was a horizontal compression. Because it only went over by 1/2 to go up by 1, we know we need to multiply by 2. This is backwards. This makes a horizontal compress by a factor of 1/2. It's the reciprocal of it. So we needed a 2 here, a multiplying by 2 on the inside to make it horizontally compressed by a factor of 1/2. All right. On a separate sheet, you need to graph this. These are your last two that you're going to be graphing. And let's hope you do it well. And we see that this is an absolute value function. We'll start with the vertex. It's 3 to the right and 4 down. This negative is on the inside. It is a horizontal reflection, which for an absolute value function does nothing. So we can almost ignore this negative that's on the inside. This 2 on the inside is going to be a horizontal, it's backwards, compress by a factor of 1/2. So instead of going over by 1 and up by 1, it only needs to go over by 1/2 and up by 1. Over by 1/2 and up by 1. And I'm making this a constant rate of change because it is absolute value. Over by 1/2 and up by 1. Over by 1/2 and up by 1. So it's horizontally compressed compared to the parent function where we don't go over by 1 and up by 1, we only go over by 1/2 and up by 1. Last one, hopefully you can graph f of x, put that on that sheet of paper where you have all of your graphs. And we have a cubic function. The vertex will be 2 to the left, not the vertex, the inflection point will be 2 to the left and 1 down. And we have a horizontal reflection. That means instead of having a point at 1, 1, that'll get reflected it'll go to the left instead of to the right. And a vertical reflection, so instead of going up, it will go down. The point at -1, -1, that's normally on that cubic parent function. This point at -1, -1, will get reflected horizontally and vertically. And cubic functions are one of the few functions that end up, when you have a negative on the outside and the inside, cancel out. Not all functions do that, but in this case it does. So it almost looks like just like the cubic parent function, just shifted 2 to the left and 1 down. All right, guys, go ahead and take a picture of all the graphs you have done on that page and submit it. And there's one more last tricky thing that I'll tell you, and then I'll let you get on to your homework. The last thing is y equals square root of 2x minus 6 plus 2. Where does it appear that the vertex is? I would say that most students would say that this vertex will be 6, 2, 6 to the right and 2 up. However, that is not correct, and the reason it's not correct is this does not fit our general function yet. Remember, our general function says that the c is multiplying times x minus h. Notice that here, the c is not multiplying times x minus h, it's just 2 times x, not 2 times x minus 6. And so if we had to get this vertex, we would have needed square root of 2 times x minus 6 plus 2. So where is the vertex really? Well, what we can do is we can factor out whatever this number is, we factor it out. 2 times x is 2x, 2 times -3 is -6, and so that's, this is another version of the same thing, and now we can see that the vertex is actually at 3, 2. This is really 3 to the right and 2 up. All right, guys, my voice is really sore. You may have lots of questions. This is one of our trickiest lessons of the year. Hopefully you feel okay about it. And after you practice your homework some, you feel even better. Feel free to come to me with any questions you might have, okay? Have a good rest of your day, and this is maybe our longest lesson of the year.